So last class we looked at the folded cascode op-amp. We looked at again the same data sheet which we did for all the other op-amps. So the DC gain was a little bit smaller than the telescopic. The unity gain frequency was the same, so that's what we have always wanted from any op-amp, which is GM1 over C. Then you had some non-dominant poles. Some poles had moved definitely, so the conductance at P1 had doubled. The capacitance was definitely larger because of larger devices. And one other thing we noticed is that noise is worse, right? Especially because M9 and M10 have to be bigger because they are now using more bias current. They are now sourcing more bias current. So M9 and M10 probably have to be bigger. So then their noise is also going to be more important. Okay. So these are, and of course again the offset of those transistors is also going to come into play. The one good thing about this compared with your telescopic is that your output swing is very, very good, right? It's the best you can do with a cascode kind of structure. Just you have 2 VDSAT from the top and 2 VDSAT from the bottom. Okay, so we have 2 more parameters. This is the 6th one. So the output swing. So as far as the input common mode range goes, what is Vmin? What is the input minimum input common mode range? Right? Very simple. Correct? VGS1 plus VDSAT0. What is Vmax? Are you sure? Remember, we've had cases like this before where it is not simply VDSAT. What is this actually limited by? This is actually limited by this voltage VBP. Right? You have VBP here and you need to have a VGS. Correct? And that again, that could be different. So you could bias VBP high enough such that M9 is in saturation, but that's not necessarily always the case. So in reality, it is going to be a function of VBP. That is what you know. VSG5. Okay. What else? Minus VSG5 plus VT plus VT1. Okay, this is the Vmax, that is the maximum common mode at the input. And one interesting thing is that this can actually be larger than VDD. Okay, because you have VT plus VBP plus VSG5, this can actually be larger than VDD. Which is a good thing, which means the input is also very good because it can actually tolerate a very large common mode range, right? It goes to the minimum, which is VGS1 plus VDSAT0. That is typically, if you have a transistor with a bias, that's the best you can do anyways. What do you think the slew rate is going to be? It's not as easy as the previous case. Obviously, previous case we just had I0, we just had a single stage, we had I0, very straightforward. Here what do you have? So let us say this current is IM1 and this is IM2. Okay. What is the current here? It's I0 plus I1 minus IM1. And similarly, you can write the current here, I0 plus I1 minus IM2. Now you can apply this limits of IM1 and IM2. What are the limits of IM1 and IM2? They can be minimum of 0, maximum of I0. Okay. I want you to go back and analyze this particular case for the slew rate. Find out the maximum current this op-amp can source. Okay, when the input is one way or the other way. I give you the answer, but I want you to go and analyze it. Tomorrow we'll discuss it to see what you have come up with. Oops, sorry. Okay. The slew rate happens to be the minimum of I0 by C and 2I1 by C. It happens to be a minimum of the two. Okay. I want you to go back and to your rooms and think about why this would be the case. Okay. It is actually, if you just look at the circuit, apply the same conditions we have before. When you have a very large DC on one side, very large input on one side and very small input on the other side, what happens to the bias currents, right? Find out what current will mirror through the mirror on the top or the bottom and so on. I want you to take a look at this. Okay? Okay. Actually, looking at this, what would you say is the well, okay, we'll discuss it when you come up with the answer, okay, tomorrow. There is one more thing about once you come up with the slew rate value, what should I1 be, right? How much should be much larger than I0, much smaller than I0, equal to I0, maybe some proportional to I0. That depends on the slew rate actually. So I want you to come up with the answer tomorrow, okay? Okay, so far we have been looking at single stage op amps. So we have pretty much, even though the folded cascode looks like a two stage, it really is a single stage, because what you are interested in is, right, you have just converted a normal cascode to a folded cascode. So really there is no big difference. You have still tried to keep the fact that the output pole is the dominant pole, right? That's what you have tried to do so far. The other topology we looked at, this was maybe a couple of weeks ago, was the two-stage op-amp. So there is one thing actually we have not discussed with the single stage. Okay, so so far whenever we have looked at the single stage op amp, we have actually assumed that, not assumed, we have found that it cannot drive resistive loads, right? Because it really kills the DC gain a lot, right? It's very good for driving capacitive loads, but it's very bad at driving resistive loads, right? Mainly because you are trying to create some transconductance multiplied by some output impedance to get the gain. If you have a resistor in parallel, output impedance, is the parallel combination of the very large output impedance which you have created and this very small load resistance probably, and so your DC gain drops drastically, right? That is our fundamental problem so far. Okay, so that is the main motivation in moving towards a two-stage topology. Okay. We looked at that also, right? If you add a buffer, you actually restrict your, what is the most commonly used buffer is your source follower. We looked at the source follower. The range, common mode range is limited. So in some way, in fact, the common mode range is limited quite a lot. If you actually put in some general numbers for VT and VDD and so on in some of these submicron processes, the swing will come out to be like maybe 0.3 volts or something like that, which is totally unacceptable, which is 1/3 of your supply. what you are normally used to is supply minus VD sat or something like that, and VD sat on the lower side, right? So when we discussed this, when we started off from the single stage, we converted, okay, so what we started off with was, we actually started off with a transconductance at the input. We put the capacitance, then we looked at the buffer, gain of 1, correct? Then what happened? We moved to an ideal op-amp with a capacitance across it, correct? Everybody remembers this? We moved to an ideal op-amp, put the capacitor so that we actually send this transconductance current through the capacitor, right? So this is called a transimpedance topology, and then we replace the op-amp again with another transconductance, correct? Okay. Now, so this is VO. So of course, GM1, GM2 are the transconductances, RO1, RO2 are the output impedances, C is the capacitance you are adding to create the integration function. What are C1 and C2? They are the parasitic capacitances at those two nodes, okay, at the output of the first op-amp and output of the second op-amp. First of all, what is the DC gain? RO1, GM2, RO2. So it is just the product of the two DC gains, correct? Okay. Suppose I add a resistor RL at the output. So now you are driving a resistive load. What does it become? So if RL is low enough, then you would have GM1 RO1, GM2 RL. So GM2 RL could be pretty small, but that is boosted by GM1 RO1. So you can still get significant DC gains from this two-stage topology. In the single stage, you could never do that because you have only one node at the output, which is the high impedance node. You are trying to multiply the transconductance by that. If you add a resistance in parallel, you have already lost that high impedance node. Okay? And the other thing is, stage 1 DC gain is not changed at all. So obviously if you had to optimize for DC gain, you'd probably stick to GM1 RO1, correct? If you want to hit a certain DC gain, you'd probably try to play around with GM1 RO1. Okay? So this particular topology is called the two-stage op-amp. Okay? And it is pretty much the most commonly used op-amp in ICs, okay, because there are lots of degrees of freedom. If you are building a custom op-amp especially, this is the most commonly used. There are other cases where just for ease of design, where your specs are not so difficult, you may choose to do a single stage op-amp. Most probably that will be either a single stage or a folded cascode. Telescopic is fairly uncommon, okay, but for very custom design, for example, for use in quite possibly ADCs and things like that, you would almost always design a two-stage, okay, two-stage op-amp. So we looked at the DC gain. To a first order, what do you expect VO by Vs to be? So first order, suppose you neglect all the non-idealities. We know what it's supposed to be. What is it supposed to be? If you neglect all the parasitics, C1, C2, you neglect the output impedances RO1, RO2, what do you expect VO by Vs to be? VO by VD. Who was that? GM1 by SC, right? That is what you are actually trying to realize. Okay. Remember, from your, when we went through the control systems model of this, we always wanted to realize an integrator. We came up with this two-stage topology because we wanted to, we had some certain constraints and we came up with this two-stage and we added the capacitor across as a transimpedance. But at the end of the day, you want to generate some GM over C kind of, GM over SC kind of function. So this is what we are shooting for, first of all. Okay. Now suppose you put down the overall transfer function. Has anybody calculated the complete one? Okay, what is the numerator? Okay, so can you tell me what the numerator looks like?
GM1 times GM2 minus SC.
Okay, okay, so that's the numerator. Did everybody do this? I specifically told you at least 3 times. Okay, did everybody get the numerator correctly? Yes, no, yes. Okay, how about the denominator? So you'll have 3 terms. You'll have some S squared term, S term and some constant term. So what is the coefficient of S squared? C times C1 plus C2 plus C1 C2. Okay. What is the coefficient of S? G01 plus G01 into C2 plus C. Okay.
G02 into C1 plus C plus CGM2.
Okay. Correct. What is the constant term? G01. Okay. Perfect. First of all, you can do a quick sanity check. What is the DC gain? GM1, GM2 over GO1, GO2 looks perfectly fine, right? DC gain looks good. Okay. Where is the 0? So first of all, this has 1 0 and 2 poles, right? That is obvious. It has a numerator is first order, denominator is second order. Where is the 0 located at? Oh, sorry. GM2 by C, and it happens to be located at plus GM2 by C. So it is a right half plane 0. Correct? Now how do you find the poles of the denominator? Assume they are very far apart. So what we'll do is why do we assume they are very far apart? Because, okay, first of all, we already know that's what we are trying to realize. Because in any multipole topology, you want a very dominant pole and you want the non-dominant poles to be very far away, right? So that's what you are trying to realize. And from the fact that we use the specific kind of topology, you should already think that we should be moving towards that. We can check our assumptions once we assume that, we solve it, we check our assumptions. If it turns out to be good, well and good, right? And I already told you, so you have x1 equals minus C by B. These are the 2 roots, right? If the 2 roots are very, very far apart, you can approximate, for the larger root, you can approximate that ax square plus bx is much larger than C. So you can write it as minus B by A. So that is, so x2 is the much larger root. X1, you can neglect the ax squared term, so it will give you minus C by B. Okay. So in this case we can write P1 and P2. What is this? GO1, GO2 over. So I'll separate the terms a little bit. GM2 plus GO1 plus GO2. Okay. Then what I'll do is I'll move back. I'll divide the numerator and denominator by GO2. Why do I want to do this? Because I want to try to bring it to a form where you can intuitively look at how the poles are being formed, right? How do we normally look at this? We know we have two nodes. We know we are going to get two poles, right? What we are used to doing is finding out the impedance at the conductance at that node, dividing it by the total capacitance at that node. Let's see if we'll bring it to that kind of form and see if that really works out, right? Okay. So what do you get? You get some GO1 by some large number. So what kind of intuition can you get from this? What is this term? It is the conductance at that node. I'll call this node 1 and node 2. This is the total conductance at that node, GO1. So that looks good. What do you see? You're expecting to see the total capacitance at that node, right? You see C1. C1 definitely appears there. C1 definitely appears there. What else do you see? It is the Miller multiplied capacitance. So you see something like 1 plus A times C kind of term. Correct? And you already know, you have studied the Miller effect, right, in the previous course? So you also get this term and you get some other terms. Okay? You can see that those other terms, for example, you get GO1 by GO2 times C and then GO1 by GO2 times C2. Those terms are probably much smaller. The dominant terms are going to be these two. Dominant term is probably going to be GM2 or GO2 plus 1 times C. That is what you expect your dominant term to be. The other things are some smaller terms because you actually have some interaction between the two sides. Correct? That you expect. Because you now have a capacitance. It is not going to be, normally if you have a completely isolated, if you have pure buffering, then you would expect the two poles to not have any connection. That is, the pole at one end will not depend on the conductance or the capacitance at the other node. Right? If you didn't have this capacitance, you would just get conductance at this node times capacitance at this node, and same thing here. Now that you have this capacitance, you will get some contribution from GO2 and C2. So that is expected, but they are small. The other thing you have to remember is that by solving the quadratic in this way, we actually made some assumptions, so that will also add some small error. Okay, but we are trying to get some intuition, and we are trying to, since they are far enough apart, it is a pretty valid assumption. Okay. Okay. One thing you do notice is that as the capacitance increases, the pole moves in, right? That is very good. Where is the other pole? The other pole is at minus B by A. Approximately minus B by A. This is minus B. Oops, sorry. This is B over A. What is that? C1C plus C2 plus C1C2. Okay? And I'm also going to write this in a slightly different way. What I'm going to do, I'm going to divide numerator and denominator by C1 plus C. Okay? What do you get? You get minus of okay. I'm going to write it, separate out the terms and write them in a specific way. GO2, because I'm going to combine these two terms. That gives you GO2. Correct? Okay, this is what it looks like. Okay, so let's try to get some intuition about this too. What is this term? What does this look like? It looks like C2 in parallel with C and C1. Okay, do you have anything like that in the circuit? You actually do. If you look at this node, you have C2 in parallel with C plus C1. You can see where that's coming from. Correct? Okay. What is this? GO2 is the conductance directly at the output. So that also you expect. But interestingly enough, that is not the dominant term. Even though you have that conductance, that is actually not the dominant term. What is the dominant term in the numerator? It's this guy. Where did that come from? Looking into? Okay. So let's rewrite this. C1, C2. Suppose I apply a test voltage VT. I want to find out the output impedance of this particular combination. What is it going to look like? So let me call this Vx. What is Vx? C by C plus C1 times Vt. Correct? What is It? C1 times Vt times Gm2. That is the current flowing in here. Correct? So you can see how this is coming out. So this is actually, if you look at this, if you look at the output impedance of the structure, it actually is Gm2 times C over C plus C1. What will you have if you had no capacitor here? What will be the output impedance? What is the output impedance here? 1 over Gm2. Okay? If you had full feedback, you would have 1 over Gm2. We have looked at many cases, where you have this kind of feedback. Okay? Whereas in this case, you don't have full feedback. You actually have partial feedback. So it will be a function of C. What happens if C is very large, or C C is very small, C is 0. There is no feedback. Yeah, it will be infinite. So in other words, it will just be the output impedance, what we had, the rest of the conductance at that node. Correct? So that term also makes sense. This term also makes sense to us. Okay? Why do you have this term? This is probably again due to interaction between the two nodes, you are getting some extra term, which in this case is not very dominant anyways. It's a very, very small term. Okay? Okay, so let us take the case where you don't have any capacitance at all. C is 0. Where are the two poles? Go1 by C1 and Go2 by C2. Correct? So let's mark that down here. Okay? You have two poles here. This is the original case. Now what have you done? Let's say you add this capacitance. Where do the new poles go to? So what happens to P2? It becomes, what is the dominant term here? It is some GM2, this is almost, let's say C is large enough such that C1 and C2 are somewhat much smaller. This is more like GM2 over some total capacitance, maybe C1 plus C2, something like that. Where is that going to be? It's going to be very, very far away. Correct? What has happened to this? You have moved it in. Correct? To a point where it is not just, earlier it used to be Go1 over C, now it is actually Go1 over C1, it used to be Go1 over C1, now it's Go1 over GM2 over Go1 times C, sorry, GM2 over Go2 times C. Correct? So it's the gain of, so now you have added the Miller capacitance, so you have actually moved in one of the poles. Okay? So this is called pole splitting. What you have done is, you have split apart the two poles by adding this capacitance between those two nodes. Okay, earlier they used to be fairly close to each other. Now you have basically moved one very far away, very far away to the, I think it is, what is the value we got for P2? GM2 over C1 plus C2, something like that. The other one is Go1 over some large C. Okay? So this is the case, ideal case which you want, right? You want to have one dominant pole and you want to have the non-dominant pole very far away. Okay? Now this kind of pole splitting obviously is very commonly used in a two-stage op-amp. Okay? And this is a common feature of coupled systems, right? Whenever you have coupling between two nodes, the coupling factor actually moves the two poles in different directions. Okay? And this may not be common only in electrical systems, there may be other systems where it's also applicable. Okay, this is just one example. Okay? So let us say I am going to draw the Bode plot of this. Let's say I am going to start off with just the magnitude. It's going to look like this. I get P1 here, omega u, and this is A0. After this you may get the other poles, right, or whatever, all the other stuff. Ideally that's what we want. Okay? How do you find out omega u? What is it? A naught into P1, right? We already know what A naught is, we know what P1 is. So I have some other terms. Okay. GO1 gets cancelled. And then now what I'm going to do is, I'm going to divide the multiply the numerator and denominator by GO2 over GM2. I have GM1 left in the numerator. Correct? Actually, let me okay. What do you get here? C. GM2 or GO2 will get cancelled, so you do get a C factor plus into GM2 plus you get some other factors. This is what we wanted. This is what we wanted, right? What did we want? We wanted the unity gain frequency to be GM1 over C. We added the capacitance C. We wanted a single pole system. We wanted unity gain frequency of GM1 over C. And to a large extent, you know GO2 over GM2 is going to be very small. So it is a pretty valid approximation. Right? It is going to be very close to what you wanted. Definitely. Is that right? Okay. So that part is good. Right? So we have verified that the two poles are very far apart. We have verified that you are getting an integrator of value GM1 over C. Well and good. Now we have some more details. Okay. We can write GM1 over C. Where was the 0? Plus GM2 over C. And the pole was at so this was P1. So this was an RHP0. We got one LHP pole at this point, the other LHP pole, this is approximate. Okay, and this was also an LHP pole. Okay, so you now have a system with, for this two-stage op-amp, you have a system with 1, 0 and 2 poles. Okay, where would you place the poles? Let us say you have P1 and P2. Okay, P1 is the dominant pole and omega u is related to that. So obviously one thing you can say is P2 should be much larger or at least definitely larger than omega u for stability. You know that, right? If you have two-stage, two poles, you want the second pole to be beyond the point where it crosses the 0 dB point. Okay, so one condition you can say is okay, this okay, that is one condition. What else? What about the 0? What does the 0 do? An RHP 0, what does it do? What is the phase shift? It's negative. Is that good or bad? It's bad, right? you know that a negative phase shift is going to reduce your phase margin. Okay, so let's write down the expression for phase margin. So let's write down the expression for the total phase at the unity gain frequency. What is it? You're going to get minus pi by 2 from P1 because P1 is the dominant pole, is very far away, right? Minus you're going to get minus tan inverse omega u over omega P2. Okay? This is minus okay, and this is from the 0. You get 3 terms. Is that right? You get 3 terms, one from each pole and 0. P1 gives minus pi by 2. P2 gives minus tan inverse omega u by, you know, right? If you have given the transfer function, you know how to find out the phase shift, right? And the 0 happens to give GM1 over GM2. Okay? This is your dominant term. Okay? So now, do you get some insight on what you need to do in the design of this op-amp itself? What do you need to do to maximize phase margin? Correct? You want to make GM2 much larger than GM1. Okay? So that is the fundamental thing you want to do. Can you make GM1 equal to GM2? You already have 45 degrees. That's actually a lot. You're giving up a lot of phase margin. Ideally, you want to have probably at least 3-4 times. Okay, GM2 to be maybe 3-4 times GM1. Okay? What about omega u by over omega P2? That is already obvious because you already know that you need to push the second pole far away from your unity gain frequency. And that will give you maximum phase margin. That is very obvious, right? From your basic controls. Okay? How would you do this? How would you increase GM2 much larger than GM1? How do you increase GM2? Let's go to the transistor level. How would you increase GM2? Current or the size. What happens if you increase the size? Capacitance increases, right? C1 and C2 will start to increase. You can't do, so what will happen is, you will shift your pole a little bit, but eventually C1 and C2 will become so large compared to C that the poles will not move anymore. Okay? So increasing the size is not a great idea. Okay? Okay? So you again come back to the same old point. You have to increase the current. Right? Same old problems with it. You increase the current, then you start hitting swing limits. The trade-offs are very similar across all of these, right? If you want higher speed, you have to burn more power and trade off with swing. Okay? Those trade-offs are very common across all the op-amps we have seen so far. Okay? Okay? Now what do you do about this guy? Can you think of some way where the 0 would become less of a problem? How would you cancel it? What would you cancel it with? Would you add another pole and cancel it? And? Add what? So what do you have here? It's actually giving a phase lag. Right? You want to try to add a phase lead so that you cancel out the phase lag due to this. That's what you want to do. Left? Left hand side 0. How do you do a left hand side 0? What gives the left hand side 0 that you know of? Why do you want to do a left hand side 0? Well, actually, the first obvious thing I would first try to do before going to a left-hand side 0 is to try to, remove the effect of the 0 completely, right? I would probably try to send it to infinity or something, right? That is the first thing I would try to do. Afterwards, you can think about bringing it back, correct, to the left-hand side. Okay, so we'll look at those two things next class. Probably that means next week. Tomorrow we'll continue with the tutorial. Okay. Now I posted another homework yesterday on which is basically, sorry?
The link is not
Really? Oh, okay. I'll take a look at it. Okay, I'll try to fix it. I thought okay. Is the basic website working? It's working. Okay. Let me take a look. Okay, I'll try to fix it. But basically, it's just a compilation of problems you have had so far. Some extra problems. Okay. So it'll probably be due sometime next week. I think next Wednesday or something. Because already at least half the problems you've already done it in several tutorial sessions. So I just compiled all of them, added a few more general problems, current sources and things like that. Okay. So we'll probably continue with those tomorrow. Then probably this weekend I'll upload control systems, what I promised a long time ago. Once we are done with this, what I would suggest is this homework we can, since it has general problems, we can push back the deadline for that. That's not a problem. We should probably get to the analysis, pole zero analysis and so on, Nyquist plots, things like that. So till I post that, you can work on these, and then once I post those, you can once I post the controls next homework, you can start working on that. We'll start discussing that next week. Okay. Okay. So we'll meet tomorrow afternoon. One more thing.